If you've lifted a heavy object underwater, it feels manageable while submerged, but the moment it breaks the surface, it feels significantly heavier. The anchor's mass hasn't changed, and the pull of Earth's gravity remains the same whether the iron is wet or dry. The difference is the water. Submerged objects experience an upward push exerted by the fluid itself, a force known as upthrust or buoyancy. This drop in apparent weight is the result of a physical interaction between the water and the solid surfaces of the anchor. To understand that interaction, we have to look at how forces behave against a surface. In physics, any force that pushes perpendicularly, at a 90-degree angle, is called thrust. Pressure describes how that thrust is distributed. It's calculated by taking the total force and dividing it by the surface area it hits. Area changes the intensity of that force. The same thrust creates high pressure on a tiny point, like a needle, but low pressure when spread across a wide surface. In the solid world, force travels in the direction it was applied, but fluids follow a different set of rules. Pascal's law states that when pressure is applied to a confined fluid at rest, that pressure is transmitted equally in every direction. Squeezing a pierced container filled with water demonstrates this. The applied pressure travels through the liquid, forcing streams out of every hole simultaneously. This behavior applies to any body of water. Liquid molecules slide and push against one another, exerting pressure on every surface of an object placed inside them. Because a fluid pushes inward from every angle at once, it creates a conflict of forces across the surfaces of a submerged object. On the horizontal plane, the pressure pushing on the left side of a submerged cube is equal to the pressure pushing on the right. These opposite forces cancel each other out, resulting in zero net lateral movement. Vertical pressure is different. It's determined by depth. The deeper you go, the heavier the water column above becomes. Since the bottom of the cube is deeper than the top, the upward thrust hitting the bottom is stronger than the downward thrust hitting the top. Upthrust is the result of this vertical imbalance. The bottom of the object is always pushed up harder than the top is pushed down. Knowing why this force exists allows us to calculate its strength, using a principle established by Archimedes. He discovered that an immersed body experiences an upward buoyant force equal to the weight of the fluid it displaces. To find that force, we multiply the fluid's density by the submerged volume and the acceleration of gravity. The physical size of the object pushed underwater matches the volume of the fluid moved out of the way, which generates the upward thrust. The strength of upthrust depends on the size and density of the liquid hole the object creates, rather than the material of the object itself. Every object in a fluid is caught in a tug of war, its total weight pulling down against the buoyant force pushing up. When an object is denser than the fluid, gravity wins and it sinks, though upthrust gives it a lighter apparent weight. If the object's density matches the fluid, the forces cancel out. This allows a submarine to achieve neutral buoyancy and hang suspended at any depth. An object's fate underwater rests on the ratio of its own density to the fluid's. If an object is less dense, upthrust overpowers gravity and pushes it to the surface. It will rise until it displaces just enough fluid to make the buoyant force match its weight, at which point its apparent weight becomes zero. This ratio is visible in icebergs. Because ice is roughly 91.7% as water, an iceberg must keep that same percentage of its mass hidden below the surface. Supporting the visible tip against the constant pull of gravity requires an immense volume of displaced water beneath the waterline. Floating is a dynamic equilibrium, a perfect balance between the weight of a solid and the omnidirectional pressure of the liquid beneath it. If you want to see more of the physics that shape our daily lives, hit the subscribe button and let us know what you want to explore next.